In our previous examples, we looked at the most basic of wind energy formulation. We looked at how to calculate out the power delivered and the power that's available in the wind. We also looked at the tip-speed ratio and how to perform some calculations around this. Finally, we looked at a problem where we were giving a shear stress that the turbine shaft could not exceed, and we were asked to determine the diameter. In this example, we're going to look at a slightly more complex problem. This time, we're going to be using the coefficient of performance that we obtain from a graph. We've got a wind turbine. It is rated at 600 kilowatts. The blade diameter of this particular device is 35 meters, and the turbine has a maximum efficiency of 45% when we have a tip speed ratio of 6. For a wind speed of approximately 12 meters per second, we're asked to determine what is the rotational speed of the turbine. This in itself is relatively straightforward to achieve. So we know the rated power is 600 kilowatts, the diameter is 30 meters, the tip speed ratio is 6, and the wind speed is 12 meters per second. We know that the tip speed ratio is equal to the omega times r divided by the average wind speed, and when we calculate this out and put in the proper figures, we find that the omega is going to be 4.114. And we'll convert this into revolutions. We will find that it is 39.2 revs per minute. The next part of this problem, we're asked to look at the overall efficiency of the device. This time we're going to have the gearbox, the generator, and the other mechanical components. And we all know that they are 45%. We're asked to determine what is the wind speed that will be required to deliver the full rated power at the terminals. Now, in this case, we do have a revs per minute. We do have an efficiency. So we need to figure out what is the coefficient of performance of this wind turbine going to be. So therefore, our PD is going to equal to Cp times a half times the density of air times the area times the velocity cubed times the overall efficiency. We're going to extract the value of Cp from this graph. And how we go about doing that is we're going to identify the tip speed ratio along the bottom edge, along the x-axis. We're going to draw a line up until we touch the 2 or 3 blade wind turbine. I say axis here, but that is actually blade. And when we do that, we're able to draw across and we're going to be able to find out what the power coefficient is. In this case, I'm finding it to be 0.49. So therefore, our power delivered is going to be 0.49 times a half the density of air times the area times the velocity cubed times the overall efficiency of the turbine. When we substitute in the correct values for each of these and perform the calculations, we're able to determine that the average wind speed in this case is going to be 5.09 meters per second. The final part of this problem asks us to determine what is the frequency of the forces on the blades for the rotational speed determined. So the frequency is equal to the omega divided by 2 pi. And when we manipulate this formula, we're able to find that the frequency will be equal to n divided by 60. So now it's only a matter of substituting in our rotational speed of 39 and dividing it by 60 to find 0.66 Hertz.